nicer feel to it.
Yeah, it's got an almost improvisational tone.
This semester on Stat 201, prepare yourself for YouTube, because we're all zoomed out. Cahoots and special guests, Tiny Brian, Puppet Shark, Evil Moobot,
I am Moobot.
Morty the Rabbit, and more. Super Statistics Bros.
What's up? How are we doing, everyone? We have audio. Oh my gosh, we have audio. How's everyone doing? Aaron, Cameron, good to see you. We'll hit a regular points button for now. I want the camera to be even more high def. We'll get that going here soon. But how's everyone doing? Little chill music. How do I get the music going to two spots? Two audio outputs. I want it to go into my headphones, and I want it going to you also so you can hear it. I should be able to hear computer audio in my headphones. You can hear the audio right now, right? So, audio output. I should have, can I put a monitor on this? Then I'm gonna hear myself. If I monitor it, I hear myself in my ears. Let's try it. Advanced properties. There you go, that's the Go XLR. Monitor on. Yo, now I hear myself. I have ideas though. No, I don't want the echo. Okay, I have an idea how to fix that. What's up, William? Good to see you there, William. Let's get started here. What questions are there? I bet we have some work to do, don't you think? Because I think tonight is one of the start early bonuses, right? Is tonight the Chapter 8 start early bonus? Oh my gosh, tomorrow night, last night was. So we have, not a lot of people have started early. I got to do the start early. I've been giving it a little bit nice lately, but Chapter 8, do you want to do Chapter 8 homework? Samantha, good to see you here. It is your call to choose what to do. It's your office hours. So what should we do? Should we do Chapter 8? Hey, Reese, good to see you here. Cameron says yes right there. And so let's get going on some Chapter 8. Got to remind people today in class, like, start early, because maybe people are waiting for me to like do this one right here. But remember, these homework assignments get a little bit more difficult. Awesome. Let's do Chapter 8. I think we can get the whole thing done before class. Yeah, it's only 6 questions. Not bad right there. Okay, let's do that. Let's go here and let's edit video for watching. Okay. We got this all going right here, and this will be 4:43. And Stat 201, Chapter 8, Homework 1. Let's go do it. Okay, here we are on the first question on the homework. A concert production company examined its records. The manager made the following scatter plot. Let's look at it. Okay, so this one's a little bit weird. Notice here that there's two groups. There's the larger venue in red and the smaller venue in blue. Now what we want to do with this, make sure I got everything over here. Oops, that's the wrong button. I got 2 hours later. I'm gonna grab a picture of this. And let's bring this over into Microsoft Word. So here we go. What we want to look at here with this relationship, how do we handle these relationships? When we do regression, what are the conditions for regression? So I like to cover a lot of topics while we're doing this. Like, you should know the conditions for regression, like bum, 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 bum. Or what is it? Who knows the conditions right here? Remind me of the conditions of regression. And I'll get a blue and red pen going here. So here we go with the, oh, we need a blue. So we need a blue. And QQ straight enough, no outliers, plot doesn't thicken. So this might have a little plot thickening, and then this one has a little outlier down there. So straight enough means the straight line goes through. Great job, Ballerina, and great job, Reese, right there. QQ straight enough, no outliers, plot doesn't thicken. So we want the plot to stay about the same thickness. 2 quantitative variables, has a straight enough relationship. They look mostly straight enough, and the bigger venue has larger values of X. So we're seeing a regression between talent cost and total revenue. So what do we got going on with this? Here we go. Describe the relationship. So weak is when the points are further out, and they're kind of tightish around it, especially the blue plot. If you take a look at what's going on with the blue one right here, the blue is pretty strong because they're tight around the line. The tighter they are around the form, the stronger it is. It's definitely positive. So we can do that right there. It's strong, definitely not negative. So we'll go with this one right here. There's one outlier from the majority. I think we said that. There was that one weird one. Good stuff right there. QQ, straighten up. No outliers. Plot doesn't thicken. So how are the results for the two venues similar? They're both positive. They're both moderately strong. Both venues show that an increase in revenue with talent costs. That looks right. Both venues show that higher talent costs causes. Now, we don't use the word cause. Cause is a bad word in this class, so never say the cause word because that's cause and effect. So that's just wrong right there, which regression doesn't show cause and effect. And there's a positive relationship. Good job, Samantha, right there with all those points. So remember, never say words like cause with regression. Cause, prove, no, we don't say those words. How are they different? The smaller venue has a less distance on the x. So right here, the larger venue has greater variability. Revenue for the venue is harder to predict. So when you look at the variability around the line, it's talking about this right here. There's more of a scatter. It's mostly linear. There's a little bit of a weird bend right there, but mostly linear. But this one has less variability. There's that one weird outlier, but the points are tighter. So the larger venue in red right there has more variability, more spread, which would be a smaller r squared. The larger venue has greater variability, making it harder to predict because it's more random. More random. That was a good question. I saw you on my friends. Oh, the locals. That's too funny. Yeah, I went to Stock and Barrel Burger, and shouts to Stock and Barrel. If you have not, who's not had Stock and Barrel before? That's too funny. Local celebrity. That's too funny. Oh man, Stock and Barrel Burger, downtown Market Square. Man, I got the Bernie. Oh man, it's so good. Like, if you think that's a photo of them like making their burgers not look good, or like they're like cheap. Oh, here's the Bernie. That is the Bernie right there. That is the burger I got. That is the Bernie at Stock and Barrel. That is the Bernie right there. It's got like whatchamacallit. It's got like berries and fried jalapenos, blue cheese, like a half-pound burger or something. No, they don't do peanut butter and jelly on it. No peanut butter on it, but I mean, if they got some peanut butter in the back, you probably could get it. And there's another burger right there with bacon and everything. Those fries look like that. I've still got some fries left over today. My wife got the what's it called? The Billy? I think that might be the Billy. Looks, man, it's so good. Anyways, check out Stock and Barrel. It's the jam. Yeah, check it out. And then they have like duck fries too. So shout out to Stock and Barrel. Really great place. I went in and someone wanted my picture. And I was like, okay. So, oh, thank you. Shout out to Natalie right there. So they're always so kind over there, and it's nice seeing people around Knoxville. And I was getting burgers, so no, well, she still works there as far as, well, not that, like, here, wait, I'm gonna, just, I don't know if they want their name on a public stream. Well, I mean, so yeah, if we just delete that one, I don't know. I'll just like, but no, it was really nice. They just went in and someone was like, hey, can I take a picture? I was like, yeah, sure, why not? So shout out to all my students and everything around Knoxville, but good stuff. All these new features on YouTube, like these hearts and everything. I can hit the heart button too. Question number 2. So I had the chicken and waffles was huge. Yeah, it's like, so I tried Myrtle's fried chicken this weekend too, or is that what it is? I think it is. They were good. They were good, but I felt like it wasn't worth the value. Like, paid a lot. But Stock and Barrel, I've got leftovers, and I just got a burger. Your live was behind. So like Stock and Barrel, I've never ate there and not felt like it's worth the value because you get this huge burger and a ton of fries, and so it's really, really good. But check out Stock and Barrel. Shouts to them. Just, oh man, I could eat their burgers every day. I probably shouldn't, but yeah. Noting a recent study predicting the increase in cell phone cost, a friend remarks that by the time he's a grandfather, no one will be able to afford a cell phone. Boom, right there. Reese already knows that's extrapolating. So extrapolating is when you go beyond the bounds of a model. Did we mark it here? We didn't draw extrapolation there, but you can see any model that you go beyond the point of the model. So if you have this right here, and then you go beyond it, you're extrapolating the model. It's when you don't have data. So think about the definition of extrapolation. It's when you make predictions outside the bounds of your what? Think of extrapolation. So memorize this definition. If you haven't, put it in your note cards. The definition of extrapolation, when you make predictions outside the bounds of your x's. So outside the bounds of your x's. That's the simple way to do it. So you're extrapolating your model. The thing is we don't know what's going to happen outside the bounds of these x's. It's so we can't really extrapolate. So he's extrapolating. If you know the word extrapolating, then you get that one right pretty quickly. We got data on 20 compact cars. Wait, got to mark the next one. But that's just the definition of the word extrapolation on that previous question. So not a hard question if you know extrapolation. Chapter 8, homework 3. Using the data from 20 compact cars, a consumer group develops a model that predicts the stopping time for a vehicle by using its weight. You consider using this model to predict the stopping time for your SUV. Explain why this is not advisable. So it's compact cars and you have an SUV. Don't even read their answers because think about this. You're predicting the stopping time of an SUV based on data from compact cars. So this is, people are asking in class, is it always with time-ordered data? This is an example of not time-ordered data. What keyword are we looking for here again? So think about how you're predicting for your SUV on data from compact cars, which probably weigh a lot less than your SUV. So don't even read, it's extrapolating again, right? So all we should do right here is look for the word extrapolating and see if it conforms to our answer. Does it not even say the word extrapolating? Oh man. This is not advisable because the model has infinite, no, not number of observations. The model is not advisable for predicting the stopping time of compact cars. The SUV is not, yeah, this is not advisable because the model predicts the stopping time of compact cars. This is not the SUV is not a compact car, so the model's predictions are not reliable measures. And that is literally extrapolation again. So unfortunately, they didn't say the word extrapolation. They're just saying like, this is not the bounds of the model. Like you're using the weight of a compact car and predicting the stopping time of a compact car. So SUVs wouldn't be in that bounds and you'd be predicting something that's not like the rest. So they allude to extrapolation with that one. And we also want to mention what we're understanding with these concepts. That's an allusion to what is extrapolation without saying the word, which is a good way to understand it. Like that was extrapolation without mentioning the word. Okay, we have a regression model right here. Now, before we do this one, we need to know how to mark the regression model. So how do we mark this? So go ahead and tell me how to write the regression equation right here using the format we write. So this is how you need to know the notation. So you should be able to write the notation underneath this. And you should be able to put something here, 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 and here. Just like the general form, what it's known as. And then we should be able to say what everything is. So what is the form of the regression equation? Remember, these are the things we should know. So we point out what do we need to know and how does it build? Because we're then going to use that to make predictions in this problem. Prediction, great job right there, Cameron. We got to throw out some bigger points. I'll throw some big points towards the end. But is the predicted value y hat equals b0, which is the intercept, plus b1 times x, meaning x is the ticket sales. Great job, Valerie, right there. So the predicted value right there, which is y hat. And so it wants us to use this equation now to make predictions. So now we take a look at what it says, and we are predicting for a 10,000 seats. So management is considering a stadium that would seat 10,000. What does the model predict the revenue would be if the new venue were to sell out? So we are saying x equals 10,000, and then just plug that in. I missed the extra credit sounding class. Oh, RotoWave, we need to get that back, right? I might be able to get it back. You know what? Let me look RotoWave right after this series of things. RotoWave makes a good point because when I transferred computers, I literally have the other computer right here. But when I transferred computers, I couldn't get the sound to work. But I bet I could do it. Wonder if. Let me see really, really quick. Where is that sound? No. Well, I'll find it after this RotoWave. We'll try to find it and get that sound back because I miss it too. I can't hear everything in my ears anymore, but I can hear some. So we're just plugging in 10,000 right into here. Solve through the equation. And RotoWave, good to see you. How is your day going? We're going to plug 10,000 in. We've got StatNation Legends here. And there we go. So we're going to subtract. There we go. We are going to make $318,776 in revenue. That's what we're supposed to make according to the model. Just plug in the 10,000. Why would it be unwise to use this model to make predictions? Ooh. Stay with me again. Notice the scale of the X right here. We're predicting at 10,000, which is way over outside of the highest value, which is about 3,100. So say it with me. We would be doing a what here? We would be doing a what? What are we doing that we shouldn't do? Extrapolating. Great job right there. We are extrapolating, making predictions outside the bounds of the X model. Let's say they want to sell out a classroom at UT. Now imagine that. How much revenue do you think they would, like imagine, let's say Keanu Reeves does a 100-person concert. Do you think he will make, because the model predicts if Keanu Reeves were to do a 100-person concert, the model predicts that Keanu Reeves would make, Keanu Reeves with his band, he's got a band, 100 times 33, and then minus 12,024. Keanu Reeves would lose $8,724. Makes my mind, I like that. Let's make that a quote. Why do you think, oh my gosh, they've changed the way this works. They've changed a lot of YouTube. So what do you think is wrong with using this model to predict a Keanu Reeves concert with 100 people? What do you think is wrong with using this model? That's going to be quote 400, I think. What is wrong with using this model to make a prediction for a 100-person concert? What is wrong with using this model to make a prediction for a 100-person concert? And I'm pointing this out because a lot of people don't realize this. What is wrong with using this model to make a prediction for a 100-person concert? Here's a 100-person concert down here. And a lot of people don't realize this. This is where a common, like, really? Comes into play. What's wrong with using this model to make a prediction for a 100-person concert? Well, not that they would lose revenue. They might lose. Well, apparently that's what the model predicts. But a 100-person concert is also a what? A 100-person concert, which they didn't even draw their line right. You're still extrapolating right there. Cameron said it. We don't have data around that number. Great job, Sarah, right there. People are saying, we got to throw out that 1,000 points because that's still an extrapolation. A lot of people think extrapolation is only on the high end. Extrapolation is any time you leave the X bounds of the model. So this is where your data's at. Your data is contained within here. This is what your model understands. And then outside of here is where you're extrapolating and you don't really have an understanding. The further out you go, the more you're extrapolating, but within the bounds of the X's where you have data is where your model understands the data and can make predictions using that line right there. When you escape it, you're extrapolating the model. You can extrapolate on the low side or extrapolate on the high side. We do have that nice word forecasting, which we use to predict things for the future, which you have to do. But the further out you predict, the less reliable your predictions are. You extrapolate. Why would it be unwise? This is an extrapolation. And so I literally just looked at the word extrapolation and clicked it. I was like, please be right. But it was the only one I saw that had extrapolation, and hence it's right. But just make sure you know what extrapolation is. It's a pretty simple concept. Just a lot of these review it. There's not a lot in chapter 8. Okay, we're gonna do some quiz questions, it looks like. Does anyone have a quiz question ready to go right after this? Because we're flying through this homework, and you should be able to get the homework done, and then we'll do some quiz questions. And they're tough. They got some My Pearson on it, but we only got 2 more. There was a strong correlation between the temperature and number of skinned knees on playgrounds. Does this mean warm weather causes students to trip? What bad word is there in that sentence? Oh, we're already seeing it. Great job, Aaron, right there. What bad word is there in that sentence? That the bad word we don't say in statistics, cause. We don't like the word cause in statistics. This is a bad word. Correlation never implies causation. So you wouldn't say it's causing it, it's just associated that when there's warm weather, people are more likely to go outside, probably more likely to skin their knees. No, in warm weather, more children go outside and play. That sounds right. That sounds right. I could just say correlation is not causation. I don't love their answers, but correlation is not causation. You can't say, even if r squared is 1, you can't say that it causes it. So that's a huge hint for the test. Gotta hear that echo because people are saying it's like super duper echo now because we reset it a little bit. A variable, I already know the answer to this. A variable that is not part of the model, a variable that is an outside variable, something that is not included in the XY paradigm, is called a what variable? Don't look at their answers. Remember, if you know the answer, and I read the first part and I can already tell you the rest of it, it's lurking. So my favorite example of this is like when we talk about ice cream sales and shark attacks, the lurking variable is summer, because summer would explain causes my, oh my gosh, Aaron, I like that right there. Summer is the z variable. So the way to think about it is you have x and you have y, and then there's sometimes a z variable in the middle that's like controlling x and y. So I'll just draw this out right here. Well, we'll answer it, we'll draw it, and then we'll do some assignments. They literally put the other ones, the explanatory and the response, which are the x and the y. So the way to think about it, can we do another practice with regression conditions, specifically no outliers? Yeah, let's find one on the, you got it, Samantha. Let's do that next. You've got x, you've got y, and then you've got z. There's not always a z, but the way it works, if we have here ice cream sales, shark attacks, and weather, it's not that ice cream sales cause shark attacks to go up. So it's not that ice cream sales make shark attacks go up. It's not that shark attacks make ice cream sales go up. It's actually that the weather is probably increasing ice cream sales and the weather is increasing shark attacks. But because of that variable that kind of connects them like the glue in the middle, it looks like shark attacks increases ice cream sales or ice cream sales increase shark attacks. But in truth, it's probably just the weather. And then we could do things to control for that. There's ways in multiple regression that we don't get into this class, but we can look for looking variables and see what truly lowers the sums of squares, all those fun terms. Well, that was a really productive 30 minutes or 24 minutes. Whoa, we're done with that. Let's go get some homework here. We're going to do a quiz question now. Thank you, Sarah. I think that's a great idea right there. Let's do one that goes over the conditions. So I'm getting a quiz question going right now. How's everyone doing this morning, though? We are like more than halfway done with the semester, right? I just can't believe it. I'm like, oh my gosh, semester's just bebopping along right here, going fast. Get to Christmas, doing great. I am excited. There's a lot. No, Samantha. Really good. Just waiting for my next class, 11:30. Hope your classes are going great. Where are the conditions? I'm gonna find a conditions one. I want to find one that goes over the conditions. Ooh. This one, I think it does some conditions. This is a tough one. We'll do this tough one right here because I know a lot of people are probably wondering about it. So let's go over here to the main screen. Oh, wrong button. Thank you so much, Aaron, right there. I appreciate that. I want Circle Drill and Band was so much fun. Oh, that's awesome. I appreciate all the positivity. That's what makes my days. People coming in here and having a good time. 100 years ago. Gotta be like 100 years ago. Trying to condition practice for the regression assignment. Yeah. So, and maybe I'll even cover the conditions right after this, Samantha. This one lightly goes over it. But here we go with the data right here. Let's take a look at it. And we first need to make a scatter plot, which is the visualization of two quantitative variables. So if you notice right here, you could kind of do it on your own. It kind of levels off at the end. You see some of these have this big drop. And actually, we might be able to identify it because this is the last year. We actually don't have to graph it. If we have to write the equation, though, we're going to have to graph it, though. Notice how these times are around where? Where's the y variable at for these times over here? Similar for the other graphics. Yeah, sure, that's fine. They're in the whats. If you look at the final times over there, Those times are in the whats. Those times are in the whats. If you look at this right here, in the later years, around 2010, 2020-ish, those times are in the whats. So we can do this one without graphing it first. We might have to graph it though. Those times right over here are in the whats. So in the years like 2010, all these things right here, the 20s. Now that doesn't mean it's the right answer, but those graphics show that. So now when we look at the data shows around 2020, the times are actually around where? The times are actually in the whats. The times are actually in the whats in the 2020s and all this right here. So the times are actually in the 39s and 40s. So the only graphic that shows that is graphic A, B, C, or D. The only graphic that shows at the end of it that it's in the 30s or 40s is graphic A, B, C, or D. The only graphic on the screen that shows at the end of it is graphic D, because all the other ones have this big drop at the end. So it has to be graphic D. All the other ones have this drop, which doesn't occur in the data. We can graph it, and we are going to have to, so we're going to see that anyways. Describe the relationship. Now this one has got me before. It's mostly positive, but I think at the end of this, it's mostly positive, somewhat linear. There's that weirdness right there. You see, I can't even touch it. I disappear when I go into the weirdness. So there's this little bit of oddness right there, that area right there where it dips, and then there's a gap because of the world wars around the teens in the mid 40s or early 40s, 42, I think. So there's gaps because of World War. And yeah, and this one, the last thing I think says it violates the condition. Let the weirdness consume you. Oh my gosh. Cracking me up. Okay, so the describe describe the relationship right here. Okay, with no races, it has a moderate amount of scatter. The scatter is how up and downiness this is right here. It's a moderate amount of scatter. It's not a lot. It's not really a good test question. It has a general linear trend, and this is the only one that mentions the gaps. So now we are going to have to use jump. So make sure to open up jump over here. Get jump opened up. We are going to have to paste the data in. So I'm going to show you how to do a regression. Then after this one, we're going to talk very specifically on the conditions. You know what? Let's do the conditions on this one, how I would analyze it, and I'll give you the in-depth explanation of it. So inside of jump right here, go ahead and first copy your data. So I click the data button and copy the data here with copy to clipboard. Copy data to clipboard. Once you've copied the data to clipboard, hit Command-C or Control-C. Notice that there are column names at the top. There's column names at the top. Now, inside of jump, you want to go to File, New, Data Table. File, New, Data Table. Since there were column names at the top, you're going to go here and go to Edit, Paste with Column Name. Edit, Paste with Column Name. Oh yeah, definitely do 320. Yeah, I'll talk more about that here in a moment, Aaron. Thank you for asking. So edit, paste with column names. I have data science minors in there right now, majors. Really good course, and you're probably doing Python. We do R. The more languages you know, the better, especially if you're doing data science. So more languages you know, the better. Because then it just kind of grows your knowledge. And I might even do some honors versions of it coming up, so stay tuned for that. I might do an honors version, which will be a lot of fun. We get to play video games and stuff, usually my honors classes. So now here we go to Analyze, Fit Y by X. Make sure the data is pasted with column names. Make sure the year and the average speed are quantitative. You'll notice because they're blue over there on the very far side in the weirdness. Excuse me. And you'll go right here, go to Analyze, Fit Y by X. And then you'll go to year is the X, average speed is the Y. Make sure those buttons are clicked. Make sure they're blue. If they're not blue, you're going to get a mosaic plot, and that's not going to be good. So repaste the data if you got a mosaic plot and they're red. Here we go. That's that same plot we saw. Now that we have this plot right here, we're going to go to the red arrow and go to fit line. And this will fit the regression line for us. So we're going to review the conditions and we're going to answer the question. So the conditions are what? What are the conditions? What? So just remind yourself the conditions, and then I'm going to explain each one for you so you can take notes or listen in. But what are the conditions? You first have to know the conditions, then you have to be able to explain them. And I'll give you a full how I would answer this on a test. QQ straight enough, no outliers, plot doesn't think of rah! Hello right there. So QQ means both variables are quantitative. If you have a scatter plot, it's quantitative. So you literally can't do regression if you don't have two quantitative variables. That's like you can't do regression if you don't have that. So we got it right here. We got two quantitative variables. So that's what QQ means, is two quantitative variables, but QQ, quantitative. The next condition is straight enough. And the straight enough condition means that this line right here is basically going through the middle of the data. If you look up here at the top of it, it does really well at the top. Like here, I'll put only that on the screen. Notice this portion right here, the line is going through the middle of it. Like the points are like the line is going through the middle of the data. That's what straight enough means. But then if I bring it over here to this side, I'll have to disappear. You can see more weirdness where it's not going through. Like right there, the line is not going through the middle of the data and the points bend around the line. So I'd say there's a little bit of an issue. If you want to go more in depth, there is a way to do this with the, oh, it doesn't give it because of the, yeah. There is a test you can do in statistics called a lack of fit test on the line. It's not on your test, and this can't be done because there's no replicates, and that's more detail than we need in Stat 201. But there are ways to statistically test it and determine if we do have a lack of fit of the line. But once again, I would say kind of straight enough, kind of, and I will mention this, don't do what I'm about to do. Do you think you can fit something other than a line? Do you think you can fit something other than a line to data? Can you fit something other than a line to data? Can you fit something other than a line? This is a polynomial, a 6th degree polynomial. Yes, there's lots of things we can fit to data, lots of different models. Don't do that. It's just, if the line doesn't fit, you could try higher order polynomial fits. You could try other things, but there are ways to fit it. And I do like this. I'll show you this. Flexible fit spline. You can actually fit a spline. And this is a good concept for you to know. What happens to r squared as I allow the spline to bend more? Look at r squared, and as it fits better, what happens to r squared? As it starts to fit better, what happens to r squared? Do you notice r squared? What happens to r squared as it fits better? Wait, as it fits better, it gets closer to 1. And when it reaches 1, the spline, the bendy line, goes through what? You lied, I like that. Let's just bet the 1,000. Wait, I lied. As it goes to 1, and r squared of 1 means that the model explains all the variation. So with all the variation explained now, this spline goes through all the whats. As it goes through every point. So that's what an r squared of 1 does, is this spline model goes through every point. You don't have to know about splines, but r squared is very important. The better it fits the model, the higher the r squared. And so the r squared is the percent of variation y explained by the variation in x. If we wrote this out as a statistical model, the statistical model would explain everything, but it's overfit, which is another topic that we won't cover right now. You can tell there's a lot of topics in statistics, a lot of fun stuff. Okay, so here's our model. Don't do that stuff I just did because that's different topics that we don't cover. So here's the model. This is the regression equation. Oh, QQ straight enough, no outliers. It's not really outliers, it's more of the bend. So I wouldn't say these are outliers. That's the non-linearity of the model. Plot thickening, it gets a little thicker here. I think, Samantha, did you ask about this? Do you see how it's a tiny bit thicker? But that's not my major issue. Like, this is really tight. Those points are really compact. And this is, like, not so tight. The moderate issue with this one is what? What do you think the moderate issue is? Like the one where we're like, yeah, a little bit of an issue here. QQ straight enough, no outliers, plot doesn't thicken. The moderate issue here is probably it has some aspect of what? Or what is the issue? We had to say, I'm a little concerned about the this of the model. I'm a little bit concerned about the what? Which condition has you most concerned? QQ straight enough, no outliers, plot doesn't thicken. Which condition has you moderately concerned? And that's the regression equation if you want to keep completing. That's the predicted value equals the intercept plus the slope. Thickening, that's this. I would be most concerned about the non-linearity of it. This wavy part at the start that doesn't follow a line, that's a little bit weird to me. Straight enough, is a bit of a concern, exactly. Now, here's a good question that you should definitely know. If we want to look at plot thickening, what plot should we look at? If we want to look at plot thickening, what plot should we look at? If we want to look at plot thickening, what plot should we look at? If we want to look at plot thickening, the residual plot. So this is the one you want to grab right here, and you're looking to see if it gets like thicker. You see how it's really thin there. You're looking to see, but you really see the non-linearity, the bend around it. So this is what you want for your assignment also. There's a little plot thickening. There's a little non-linearity. The non-linearity because it goes wee and bends around it. The plot thickening because it's really thin in here. By thin, I mean the widths of these points. And it gets a little thicker right in here, and it gets thinner, but it's, yeah, there's ways to test all these, but it's all right. It's not the worst regression I've seen. It's not the best. And my Pearson, I wish they just, like, subjective questions are hard. Make sure to throw your negatives. If you forget your negatives, you lose points. If you don't round properly, I'll give you the points back. Negative is very important. Rounding is whatever, but the negative signs are very important. 2 decimals. Is there a plot condition thing where we can draw a cone shape? Yeah, exactly. And we'll try to make it obvious on the test. Usually we give ones that are ridiculously obvious, especially in this class. We give ones that are very, very obvious. And so this one right here, I can't remember. No, the relationship is not straight enough in the early 20th century. I think it's this. You see, you can't say the conditions are met because, yes, it's not straight enough. That doesn't make sense. No, the variables are quantitative, and the plot seems to be straight enough to fit. But there are outliers, so not really outliers. Yes, the variables. So it's either this or this, and I think it's this right here. Wait. The answer. Yay, we got it. That's a good tough one. That's a good tough one right there. Does that make sense, Samantha, right here? It's the non-linearity in the early part of the 20th century where it does that little bendy part. So that's the non-linearity right there. So this was a really good question, probably a tougher one for a lot of people. Glad to get a lot of these really tough ones done. This one right here, also giving stuff. This one's a tougher one. We'll do all these big part ones. 38, 53, Stat 201, Chapter 8 quiz. Is there any evidence? Okay. Is there any evidence that an animal's gestation period, how long it's pregnant for, is related to the animal's lifespan? The scatter plot shows the gestation period of versus life expectancy of 18 mammals. The highlight point is the humans. So are humans different from other animals? Are humans different from other animals? Just look at the model. If you think about a line going through this data, just still stay on the screen when I take screenshots. That feature. Humans are different. And we are definitely a what? QQ straight enough. No outliers. Plot doesn't thicken. We are definitely a what if you include us in this model. So here is the human line with humans included. And here's the non-human line. We're going to have a pole. We're going to decrease the slope. The R-squared is probably going to get worse. We're definitely an outlier. So if you do include humans, it's the red line. If you don't include humans, it's the blue line. Because the line will go through, it'll try to minimize the sums of squared error. That's what it tries to do. Basically, in regular terms, it tries to get as close as it can to every point, like passing through the middle of the data. So the points kind of pull the line towards it. And like without saying reduction of sums of squared error and stuff like that from the naive model. For these data, the R-squared is 54.2 because whenever you, oh, that's R, sorry. I already treated like the other concept. Do you think the association would be stronger if humans were removed? So the way to view this is to draw a density ellipse. Draw the density ellipse with humans, and draw the density ellipse without humans. Oops, I changed colors. The water this is, the stronger this is. The water this is, the stronger this is. Like this versus this. The water this is, the stronger this is. The water this is, the stronger this is. Like it's stronger when the density ellipse is tighter. A density ellipse means draw around it. Closer, tighter. So it's a lot stronger because the points are tighter around the line. So great job right there, people following along. So if we remove humans, it'd definitely be stronger. both the slope and correlation would increase. Increase in slope isn't stronger. Increase in correlation is, but it is true the slope would increase. But slope, you could have a weak relationship and points be scattered out. So come on, my Pearson. Get with it. Get with the program, my Pearson. Is there any reasonable justification for removing humans? Can you remove outliers? Yes, you can. You always need justification. So yeah, let's just like do non-human species. Now this is where you basically see jump output right here. To review the jump output we just had, you can see the parameter estimate right here. And that is where you see the name of the variable over here. And let me make it so you only see that so it's very clear what I'm pointing to. Okay, so we're going to go right here and make this look like this. And there we go. So this output right here is the same thing. Does that make sense? So you've got intercept, which is their constant. You've got year, which is this. And then the coefficient is the estimate. They're only giving you this portion right in here. You don't really need the standard error right now, or the t-ratio, or the p-value. I mean, they are kind of important. But right now, we're just writing out the model. So this value up here is the intercept. So in notation, what is this value? In notation, what is this value right here? It's the intercept, so I want the notation of that value. Like the y hat, the x, that is the intercept right here that I'm pointing to. That is the intercept. So what is it in notation? Remember your regression equation notation from earlier, and think about what is that in notation, the intercept. This is a different model, but what is the intercept in notation? You have to write y hat equals b0 plus b1x. So the intercept as notation, when we just write it down as a like value where we're going to put it in later, the value of what? What is the value of the intercept? Just in notation, like is it x? Is it y hat? Is it b0? Is it b1? What is the value of the intercept? It is b0. Great job, Samantha, right there. It's b0. So let's look at what they want to ask us. This is b0, and below it is b1. So b0, b1, intercept slope. Yep, b0. Because it's when x is equal to 0. Just remember it that way. When x is equal to 0, we expect y to equal b0. For each 1 unit increase in x, we expect y to increase by b1. So is there an association? Yeah. Moderate, strong. Not perfect. Perfect, I mean, goes for every point. Moderate, strong. Interpret the slope for each. Just duplicate that. Duplicate it everywhere. For each additional year of life expectancy, for each additional year increase in life expectancy, the gestation period increases by about, and the slope is this one, 12.96. Certain mammal has a life expectancy of 29 years. So this is where we need to use the slope. And we're just going to go here and go 29 times the value of the slope. This problem is harder. And then add that to the intercept. Holy mackerel. That's the gestation period. So yeah, we just times the value of 29 times this and add it to the intercept. And don't round to 1 decimal place now. So we just go here and round to 2. Check answer. We got it. Would it allow me to round a little bit weird? It's got a plus or minus. That's nice. So there's usually a little bit of leeway. Does that make sense? The question looked really long, but really nothing too bad on it. It's at the end of it, it's solving the regression equation. The question is basically, or this one reviews, can you remove outliers and writing the regression equation? Because the regression equation right here is b0 plus b1, b0 plus b1, and then input x right there. The x value is 29. So, and also what you could do, you could go to where 29 is at and draw up and over, and you'll see it hits about here at the 400 mark. So there we go. Let's do another one, trying to get as many done as I can right now. Oh man, this question looks crazy long, but I bet we got it. What are we seeing down here in the corner? So is the test going to have something like this problem? Like that one I think could be on the test. Like I'm not saying it is, but a format like that. This one right here also looks formatted. Yeah, this looks like a good test one. I think because we can't have you do things with jump on the test, so we can give you output. This is another good one. Let me mark it here in the notes. But this is another good, I would say it looks so far. I'm trying to remember this one off the top of my head. 46, there we go. Another good one that would be good practice for the test. Some of them are, you gotta know what you're trying to learn and then think about how does it relate to the test. So I'll try to always give you the key things that would be test related. Like when you make a regression plot, you can make a what of it. So when you make a regression plot, you can always examine your what's of the plot. And look at that really random one over there. When you make a regression plot, you can always make a residual plot. Now, there's a lot of different ways to do residuals. I like when you make the line flat. That's the easiest one to do. Some of them, they do like a time order, or they do a versus predicted value, but I just prefer to make the line flat. It's my favorite way to make a residual plot. If you look at the jump output when we did it, there are lots of different ways to do residual plots. There is, like, every one of these is a residual plot right here. Notice how it says residual there, residual there, residual there. You only need the top one when you're doing yours. So sometimes they show you a little bit different in one, but my favorite one is take the line, make it flat, which this one is right there. So Puppet Shark in the class, yeah. And so with this right here, are the conditions for regression satisfied? QQ, straight enough, no outliers. So Samantha, good review right here. What major issue do you see, especially in the residual plot? What major issue do you especially see in the residual plot? You can't see it now, but now you can. And not so bad here. The line goes through the center of the data. Major issue over there. Major. That's how we would do it on a test. This is very much like it would be the outlier. Great job, Valerie, right there. That's how we do it on the test, is we'd put something very extreme where it's like kind of obvious when you look at it. So the residual plot with no evidence of linear, it's linear. The plot shows strong evidence of nonlinearity. Oh, no evidence of nonlinearity. Plot shows contain. Plot has much more variation for no. The residual plot contains clumps, so it's no. No. The residual plot is reasonably scattered with no evidence of nonlinearity. Is it not going to mention the outlier? The residual plot shows strong evidence of nonlinearity. I don't see the nonlinearity. The residual plot contains clumps. It doesn't? Yeah. They'd better not say it has more variation at the larger predicted values. I will almost call my Pearson, because maybe, yeah. So I really think it's A. Oh, is there an outlier? Yeah, that's the first thing we saw. If so, identify what the data value is unusual. Select the choice below. Necessary fill in the blanks. So yes, there is an outlier. So the outlier is unusually high. If you were to fit a model right here, it's much higher at the x of round to 1 decimal. I gotta zoom in here. That's about at 7.8. 7.8. I hope it has a little bit of leeway. It's an all right question. Not loving it. Interpret the value of r squared. Now here's the thing. This is one we should know like that. For 1,000 points, 7.7. I bet it'll accept either. I'm going 7.8, but I'll see if it takes 7.7 right after. On the test, I'd give 7.7, 7.8. Don't say like 8, but probably give 7.9 to be nice. Like 7.6 to 7.9, 1 million points. Interpret the value of r squared. Here is r squared right here, already given as a percentage. But remember, you need those things above my head, but you should be able to do this for the test like that. So who can do the value of r squared right here for 1,000 points? You need to know that thing right above my head right there. Who can give the r squared interpretation? Know how to do your r squared interpretation. Blank percent of the variation in y is explained by the variation in x. So it's 68.7. 68%. Not if though. If retype it, Cameron. Good practice right here. Not if though. So type the full thing. Remember this. I want on the test. You're like, boom. I want you to get all those points. You see it on the test. Get the 1,000 points. I want you to on the test be like, I want you to do it one more time. You got this. Got that the full thing though. Full thing. Full thing for the points. So when you get to the test, you're like, I've done this so many times. This is a joke. 68.7% of the variation in life expectancy is explained by the variation. Is explained by. Let me see. Valerie said 68% of the variation in life expectancy is accounted for by the regression. Kind of. Is that what they put? Is that what they put? I don't like that. It's all right, Valerie. I'd probably, my greatest sale points, I'd probably give that for you because the regression model explaining it. No worries. And so I'm going to give the 1,000 points right here. Here's my answer. You ready? This is what I put on the test. There are other ways to do it, but I would still keep to like this just in case because it's blank percent of the variation in Y is explained by the variation in X. So 68.7% of the variation in life expectancy is explained by the variation in fertility right there. So I would use that right there. That is the best way to make sure you get all the points. If you feel like the grader wasn't fair, let me know. So what did they put? Means that 68.7% of the variation in life expectancy is accounted for or explained by the regression model on birth rate, but explained by the variation. If government leaders want to increase life expectancy, should they encourage women to have fewer children? That's a cause and effect sort of idea. Nice job, Jennifer, practicing another 1,000 points. Thank you, Jennifer, for that practice. Although there's an association, there we cannot say causation. Lurking variables could be in play right here. So the biggest thing is, can we use this as a cause and effect relationship? The answer is no. Did we get everything right? Because I'm a little worried on that first one. We did get everything right. So the first one, yeah, I mean, it is a good regression model, other than the outlier. But they should have mentioned the outlier to start. I would say there's an issue with the outlier. I would definitely point that out if I was doing this. We'll do this one pretty quick. Are there any like freebie ones? I was like doing the freebie like true falses and stuff. Is there another? Oh my gosh. What is wrong with this residual plot? After keeping track. What is wrong with that residual plot? You should be able to see it very quickly if you've done a lot of these. What is wrong with that residual plot? Definitely not linear. It's like you see that and you're like, whoa, there's a bend around this. I think this one's got me on one part because it's like the predicting about average temperature and residuals. Yeah, I'm not going to make the mistake on it this time that I've made. I've missed a question on this before, I know. That's line, oh dear. There's a bend around it. Remember, this is a residual plot, which means you've made your line flat because the line has been set to 0. It says residuals, and that is a residual plot. Make sure to review chapter 8 where we go over residuals. Interpret the slope of the line in this context. So for each additional increase in temperature, we expect the cost to increase by 1.88. There it is right there, an increase in heating cost. Interpret the y-intercept. When temperature is equal to 0, we expect the cost to be, decrease. Decrease because it's negative. Sorry about that. Make sure to do the negative or the positive. Interpret decrease. Cameron earning everyone another 1,000 points, I think, because I'm letting in the future. But yes, good catch. The model predicts a heating cost of 103 when the temperature is 0. Remember that the intercept value is this right here. That is B0, and it's when x is equal to 0, right there. During the months when the temperature stays around 32 degrees, would you expect the cost predictions of the model to be accurate, to be too low, or too high? This is where I make an error. 32 degrees is right here. And although it bends, you can see it's too low. See that point right there? The model is too low because, the model is too high, the point is lower, the residual is negative. So if there's a negative residual, it's below the model. So here's your model, here's the point, and even if we make the line flat, the point would still be below the model, which is the line. So would you expect your predictions to be, they'd be too high because the residual is negative. What heating cost does the model predict for a month where the average temperature is 10? So what do? How do we use this up here to predict the heating cost when the temperature is 10? How do we use this? Plug it in. So we go right here and we type 10 times 1.88, and that's going to be subtracted from 103, and there it is right there. During one of the months on which the model is based, the average temperature did average 10. What were the actual costs for this month? So if you look right here, the residual, they're going to have us do that, are they? So the residual is what? Just look at the residual, negative or positive. We're looking at this point right here, and it's negative or positive. It's negative or positive? Negative. that means it's below the model. And it looks to be about negative what? It looks to be about negative what? This is a good question. It looks, until I get one of these parts wrong, and then we end office hours. It looks to be about negative what? Negative 3, right? So that means the actual value is 3 below our model. Does that make sense? Like, if it's below the model because it's negative. So that means we take the model's prediction and we subtract 3 from it. So round to the nearest dollar, that's why they're doing that. Does that make sense? Since it's negative 3, it's 3 below the model. Cameron sees it right there, like, oh, it's 3 below the model. The model predicted 84.2, so if it's 3 below the model, subtract down to get to it. So really, if you get that, you're doing really well. Do you think the homeowner should use this model? No, because the non-linearity. Would this model be more successful if it's in Celsius? No. The units don't influence the model. Cross your fingers, everyone. Woo! I even got a little bit where the model has some use. Fit a polynomial model and it'll increase the R squared. But I was like, you could kind of use this model, especially if you know how it misses. All models are wrong, some are useful. George Box right there. So really good questions. We did a lot of the harder ones. I think we got a lot done today, especially during office hours. We were really just moving along here. So I mean, especially if it's extrapolation. Student wrote, I know the model is correct because my R squared is this. No. The scatter plot should be examined first. Does this model allow the student to make accurate predictions? Yes. Higher square value always leads to accurate. I mean, that's a really high R squared. The word always is really worrisome, though. Yeah, that's okay. Yeah, the word always is a scary one. I don't know. You explained 99.4% of the variation. I'm trying to think of how I could make something that does that. Yeah, I could see it. It could be some extreme outlier doing it. So, with that, we'll have class here in just a little bit. I'm going to go grab a snack. Bye for now, everyone. Bye.